Hi everyone. Today we are going to start studying about the advanced control on the topic of a lead-lag compensator. So what exactly is a compensator? In control system design, modification of existing plant dynamics or hardware system is usually very difficult because the plant may be fixed and it could not be modifiable. Even if you want to change it, most probably you will need to spend a lot of money in order to do that due to the downtime or replacement of hardware components. Therefore, a more viable solution if you want to fine-tune or change the response of the whole system will be to change the software, or what we so-call controller and compensator. Controller and compensators are almost identical to each other with very minor differences between the two of them. Right, so what exactly is a compensator? Compensators, it functions by adding the poles and zeros to current system so that the compensator system has a root locus that goes through the desired pole locations for some value of gain. Right, so in this case, this satisfies the required system response specifications. So in short, what does that mean is that first we know we have a desired pole locations. Okay, we know these desired pole locations because that is the behavior that we want the system to have, and therefore based on our desired pole locations, when we design the compensator, we add the poles and zeros to the current system in order to change the behavior of the system. Right, when we design for the compensators, these compensations, it can be either in cascade or feedback configurations, and this could be realized through the electrical compensating networks, and the compensator supplies an additional phase angle to the system and alters the gain. And phase lead compensator, it always use positive phase angle, whereas the phase lag compensator, it produce negative phase angle. So we are going to investigate further into this phase lead compensator and also the phase lag compensator in the following slides. So what exactly is the differences between the two cascade and the feedback configurations? We have our initial control system, which consists of the original controller and the plant. And if we want to change the behavior or the response of the whole system, we can add a compensator and cascade it in front of the cascade in series in front of this initial system. So this is what we so-call as a cascade compensators. Right, on the other hand, in this second block diagram, we can see that the initial system, the initial forward path is left untouched, and what we are doing is we add a compensator in the feedback loop, or what we so-call as a feedback compensator. So in this case, this gives us the feedback configurations. Okay, so just take note that design procedures for the feedback compensation is usually more complicated compared to the cascade compensations. However, there is one good thing about this feedback compensation is that it could give us a faster response and it may not require additional amplifications. However, due to the complexities of designing the feedback configurations, therefore in our study we will be totally concentrated in the feed-forward or the cascade compensator configurations. Design of a compensator usually involves two main approaches. First is based on the time domain, and the second is based on the frequency domain. Both of these approaches require us to set several specifications. For time domain design, it requires us to determine the specifications includes the transient response indices. These indices describe the behavior or the response of the system prior to the settling, including overshoot, rise time, settling time, and so on. And in frequency domain design, on the other hand, it requires us to set the specification which includes the gain margin, phase margins, and also the resonant frequency. All these parameters or the specifications are important for the stability of the system, right? So if we want the system to behave more steadily and then is more stable, less oscillatory, then most probably we could design it using the frequency domain approach. Compensator design based on time domain specification is usually carried out using the root locus technique. As for the frequency domain specifications, this design is carried out using both plots. Okay, so phase lead compensation, or what we so called as a decontroller, it improves the transient response of a system without affecting steady state error. Whereas for the phase lag compensations or the I controller, it improves the steady state response, and it also at the same time reduces the steady state error, and these do not cause changes to the transient performance. And in summary, we can say that for the first lead, the main purpose we design a phase lead is to change the transient performance. Okay, and whereas when we want to use the phase lag compensations, the main use of it is to reduce the steady state error. Alright, and also to improve the stability of the system so that it shows less error. This slide illustrates the hardware realizations of the phase lead compensators. As you can see in these figures, phase lead compensator can be achieved using the RC filters, which consists of two resistors R1, R2, and a capacitors with the capacitance of C. The transfer functions of these RC filters is clearly shown in here, and the derivation of it you may refer it back in the instrumentations low pass or high pass filter that you have studied before this. Alright, and by assuming that alpha is equals to 1 over R1C and beta is equals to this statement, and therefore we can see that the transfer function is now equals to S plus alpha divided by S plus beta. In order to have a phase lead compensators, the alpha value should be less than beta, and by having this alpha less than beta, it means that the imaginary plots for this transfer function will look something as this, where the alpha, which is a zeros, will be placed rightwards of the poles, which is the beta. Okay, and both plots on these transfer functions, you may see that the alpha, the breakaway point is for the alpha happens earlier at a lower frequencies compared to the beta, and therefore the response will be moving upwards, increase in gain, and at the beta it will start to settle down, right, and steady down. Okay, at high frequency, the phase angle changes will be happening in between of this alpha and the beta. Alright, and the phase angle relationship is given here, and just take note that the phase angle V is always positive, right? This is always positive. Decontroller is indeed a very special case of a phase lead compensators. We know that the transfer functions for a decontroller is equal to KdS, and S is in the numerators, and therefore this gives us a zeros, which is at the 0 point. Okay. For phase lag compensators, the hardware realizations of it could also be achieved through the use of RC filters. So in this case, we are using two resistors R1 and R2 plus a capacitors with the capacitance of C, and therefore the transfer function derivations is clearly shown over here, such that we can assume that the alpha is equals to 1 over R2C and the beta is equal to 1 over R1 plus R2C. Just take note that this alpha and beta will have a different value as that in the phase lead compensators. And therefore, assuming this alpha and beta in this case will give us the transfer functions which is very similar as that shown in the phase lead compensators over here, which is S plus alpha and S plus beta, right? So the only difference is that in this case we need to set that the alpha must be greater than beta in order to achieve the phase lag compensators. For the phase lag compensators, alpha is greater than beta. We plot it in the imaginary plottings. We can see that the zeros will be placed left side of the post. Okay, so the post will be at the right side, and the both plot of it further show that the both plots will break at the beta frequencies, and then we will settle down, and then at the another breakaway point will be the alpha, and the phase angle changes will change in between of beta and alpha, but just take note that the phase angle is always negative here. Alright, for similarly for these phase lag compensators, another very special versions of it will be the integrators. So we know that the transfer functions of a integrator is actually equals to Ki over S, and therefore we have a post which is placed directly at the point of zeros, which gives us the I controller. This example illustrates how we could use the phase lead compensator to change the transient response of a system. And given that the open loop transfer functions of these uncompensated systems are given by these transfer functions, and consider that we are going to apply a phase lead compensators to this system in order to improve the transient response of the systems, and the transfer function of this compensator is given as this, right? Exact computations on the how we determine these 0.5 and 7 will be shown in the following lectures, but in this example we will just see how will this phase lead compensator affect the transient response of the systems. And this is a phase lead compensator simply because the alpha and the beta, alpha is less than beta. Okay, the root locus on this compensator system is shown in this slide, and you may see that for the SEMM damping coefficient zeta equals to 0.7, we draw a straight line up. Right, this is a 0.7 line with the damping 0.7, 0.7, and you may see that this actually causes the whole graph. Okay, blue is the initial system without the compensators, and after adding in the compensator, the whole root locus is pushed leftwards. Okay, it is pushed to the left, and this means that the compensator systems is faster. Right, compensator systems, the transient response of this system is faster as compared to the uncompensated system, which is situated at the right side of it. But this is at the expense as that the K is also increased from 1.61 to 35.5. Initially, without the compensations, we get the gain is equal to 1.61, and this is further increased to 35.3. By applying the system gain K equals to 1.61 for the uncompensated system and K equals to 35.3 for the compensated system, and we will obtain the both plot of two systems as shown over here. Right. So for the gain margin, you may see that both of them are actually there are not much changes, 20.4 and 21.9. For the phase margins, the compensator system has significantly increased, okay, under the SEMM zeta equals 0.7. Why we know that both of them are having the same zeta? Simply because we are using this system gain 1.61 and 35.3 into the calculations for this both plot, and these two Ks are obtained while the damping is actually under 0.7. Okay, so you may see that the phase margin, which is initially for the uncompensated system, is 64.1. Now it is greatly increased to 87.6. Alright, and to show the transient response of these two systems, we get a time plot, and this is obtained. This is performed by using the MATLAB Simulink, and by using this, constructing these Simulink block diagrams, and you may see that for uncompensated system, K equals to 1.61, it has a overshoot, and the response is much longer, much slower as compared to the compensated system once the K is now 35.3. And you may see that the response is faster, and at the same time it eliminates the overshoot of the system. Okay, and therefore we may say that the overall of this system has been the overall transient response of this system has been significantly improved. That's all for these online video lectures, and hopefully it is helpful for you in the understanding of fast lead and fast lag compensators. Thank you.